This tutorial is a little different because I've already written everything out for you, but I'm going to talk you through it. I want to discuss here the spring force between a nucleus and an electron cloud. This is a model that we are using that eventually leads us to being able to make an estimate of the radius of a hydrogen atom. So over here what I'm drawing is a little X over a red dot, and the white here indicates an electron cloud as we've drawn in class, and the X marks its center of mass. And then the nucleus I'm representing with this red dot, which you now can see. Now, if an electric field is applied to this atom so that an electric field is oscillating back and forth like this, we'll transition to a different situation where say the red dot has stayed in exactly the same place, but the electron cloud has moved over a bit. This is a gross exaggeration of how much, but you've got some sort of displacement. This cloud has a radius which we're going to call capital R. Not that that's going to show up later, but you can use that variable when you're solving this problem. We can now think about what's the attraction between the center of the electron cloud and that nucleus. And the easiest way to think about this problem is to forget about the nucleus for a second and just think about this ball of electric charge. Let's move over to here, where again, here's the center of the electron, but we've zoomed in a lot, so there's electric charge everywhere in this region. We're in the center of a big ball, and we can ask ourselves the question, at a point in space where the proton, the nucleus of this hydrogen atom, the proton would be, what's the electric field there? So that becomes a question. Forget about the nucleus for a while, just ask what's the electric field at some distance r from the center of the electron cloud. Our reasoning can follow the tools that we built up in class. One thing we know is that the divergence of the electric field everywhere inside of this ball is the charge density at that location divided by epsilon naught. Well, let's model this ball as being a constant density ball of charge. So that's an approximation, of course. The whole thing is just a gross simplification of what a quantum mechanical atom electron cloud really is. But let's model this ball the simplest possible model. We just say that rho is constant within the ball. So we now have a Maxwell equation telling us the electric field has to obey a certain behavior. Its divergence has to be constant everywhere in this region of space. What's another thing we know? Well, this is going to have a problem, has spherical symmetry. We have a sphere here, and we're looking for an electric field caused by a spherical distribution of charge. So we look on the Griffiths page, or wherever you want to look this up, for what the divergence of any sort of vector field E is. And what we find is that there's only one term in the divergence which depends upon the radial component of the electric field. And since our electric field only has a radial component by spherical symmetry, this is the only term that matters. So the divergence of electric field is given by this expression over here, 1 over r squared, and then a derivative of r squared times that electric field component. Now you compare these two lines, and that tells us that this whole expression has got to be a constant. Well, if this whole expression is a constant, the thing in red here has got to scale as r squared in order for it to multiply by 1 over r squared and be a constant. That means that the thing in blue has got to scale as r cubed, because when we take its derivative with respect to r, we'll get something that goes as r squared, and then that'll cancel out the r squared. And that means that the thing circled in white here has got to scale linearly with r. So we now have that the electric field R, electric field as a function of position, has got to be a constant at best times R. Now we'll imply one more thing, which is a boundary condition. I mentioned in class that divergence only tells you how the electric field changes with position. It doesn't tell you what the electric field is. In the context of this problem, that would be like saying, hey, I'm taking a derivative here, so this thing in blue could always have an arbitrary additive constant. That means E of r has an arbitrary additive constant. And that's true. So what's our boundary condition? Our boundary condition is that by symmetry, there can't be any preferential direction of an electric field right at the center of this spherical ball of charge. So at the origin, when r equals 0, the electric field's got to be 0. Given that the electric field is a constant times r plus an arbitrary constant, the arbitrary constant additive must be 0, because that allows E of r to be 0 when we're at the origin, when r equals 0. So now we're all set. We now know how the electric field of this ball of charge behaves as a function of position. But we don't know what the constant is. Now, if we actually evaluate this original yellow expression, the divergence of E equals all of this, we get that it's equal to a constant times 3. 3 came from taking the derivative of r cubed. We got 3r squared. Well, we have a constant times 3 equals div of E. We also have rho over epsilon naught equals div of E. Combine those two equations together and we can now have an expression for the constant. Now, what's rho? I'm not going to give it to you explicitly, but it's two things that we know very well. The charge of one electron, you have to look up the elementary unit of charge in coulombs or whatever, and it's negative, of course. And then the volume of the ball, which has a radius capital R. That's what we want to solve for in your homework. What's the radius of this ball? So the electric field, again, is some constant times r in the r hat direction. So the force on the proton, on the nucleus of this simple hydrogen atom, is going to be the charge of the nucleus, which is positive E. E is the elemental charge unit, times the electric field, which is going to be electron charge times constant times r hat. And this shows us that the force of attraction between the proton and the electron, because this is an expression for the force, it obeys a law of force equals negative k times r. The negative just comes out of keeping track of the negative charge of the electron and the positive charge of the proton. So we get an overall minus sign. The constant and that E give us the value of k. And this is important. This allows us to assert that as you apply an electric field to an electron cloud surrounding a nucleus, that restoring force that the nucleus is pulling the electron cloud's center of mass back to the center is spring-like. And we will leverage that on your in many places in the course, including on the homework problem, where we will figure out what the radius of this ball must be in order to agree with experimental data about the sort of resonant frequency that hydrogen atoms actually show when you shine light on them. What wavelengths of light do they absorb?